In this video, we are going to look at example 2b from page 486, which deals with the intersection of three planes. Now, three planes can intersect in a variety of different ways, and you'll see some pictures on the right of the screen here. They can have one intersection point intersect in a line. They can all be coincident and the same plane there. They can be parallel and distinct. There can be two parallel planes, or they can intersect in pairs. So the first thing I'm going to do is analyze the normals of my three planes and look at their relationship to each other, and this should give me an idea about which cases I might have and which cases I can eliminate. Looking at the normals, I noticed that none of them are scalar multiples of one another. If none of the normals are parallel to each other, then none of the planes are parallel to each other, which means I can eliminate that one, this one, and this one. So I'm left with three options. And there's something that differs in each of these three. In option number one, the normals are not coplanar. But in options 2 and 3 here, the normals are coplanar. So I'm going to test if N4 and 5 and N6 are in fact coplanar, and that will help me to eliminate another possibility. Remember that to test for whether or not the normals are coplanar, you need to find the triple scalar product, which means you need to dot two of the normals and cross two of the normals. And while it doesn't matter which order you put these normals in, it does matter that you do the cross product before you do the dot product. The cross product of N5 and N6 gets me 17, negative 17, negative 51. And if I dot that with N4, I get an answer of 0. This means that the normals are coplanar. So I can eliminate one more potential case. So my planes either intersect in a line and have an infinite number of solutions, as in this case, or they intersect in pairs and there's no solutions, as in this case. So my approach to figuring out which option of those two is true will be to algebraically verify whether there's a solution or not. Here's my strategy. I've got three unknowns with three equations. I'm going to use elimination to find two equations with two unknowns. Then I'll use elimination again to find one equation with one unknown, and I'll see what happens in that equation, whether or not I have a solution or not. So I'll start by labeling my equations. Let's call them 1, 2, and 3. 1, 2, 3. If I subtract equation 2 from equation 1, I can eliminate x. So that'll be my first step. Subtracting, I get negative 12y plus 4z minus 16 equals 0. And I can actually make that equation simpler if I divide every term by 4. And I'll move the constant over to the other side. I'm going to call this equation 4. It has two variables in it. So I'm going to do the same thing now, eliminate x, using equations 2 and 3, so that I'll have another equation with two variables. In order to eliminate the x from between equations 2 and 3, I need to take equation 2 and multiply it by 8. Subtracting these, I get 51y minus 17z plus 68 equals 0. And again, I can simplify this because each term is divisible by 17. And again, I think I'll bring my constant over to the other side. And we'll call that equation number 5. Two equations with two unknowns. I will use elimination between them to see if I can find a solution for one of the variables. If I add these equations, I'll be able to eliminate y, but you'll notice I also eliminate z. And the constants become 0. And we know that this equation has an infinite number of solutions. And the only way to have an infinite number of solutions is if the planes intersect in a line, given that the normals are coplanar. So going back up to our cases, we've just eliminated this possibility, and we know that this is our situation. So what's left is to find the equation of the line that defines all the intersection points. If you recall from example 1 in the textbook in this section, we can go back to one of our equations that only has two unknowns, so either equation 4 or 5, and we'll set one of the variables equal to the parameter. Looking at equation 4, I think it would be easiest to set y equal to t, because solving for z in terms of t will then be a very easy procedure. So let's let y equal our parameter t. And then we'll sub that into equation 4. Negative 3 t plus z equals 4, and just solve that for z. Once you have y and z, you need to go back to the equation that has 3 unknowns, which is any of the 3 equations we started with. I'll pick equation 1, and I'll sub y and z into that equation in order to solve for x. Expand and simplify in order to solve for x. And there you have your parametric equations, which we can write using our brace bracket. And we can conclude that the planes form a consistent system, which means that there are solutions, or there is a solution. As well, the planes all intersect in a line, and we can give the vector equation of that line. Our R0 comes from the parametric equations 2, 0, 4, plus t, and then our direction vector, just the coefficients of the t values in the parametric equations. All done! Yay!